Welcome back. So let's continue where we were. I promised to you the chase algorithm. Again, what is that? It's a way to tell whether or not, if you decompose these tables that are breaking the Boyce code normal form into smaller tables, if you join these smaller tables back into a big table, do you get back or do you not get back the original table? And there is an algorithm that allows you to do that without looking at the tables, just with the functional dependencies and the reasoning on them. It's actually quite intuitive, you will see, so I will drive you to that. So let's start with the easy side. We want to see, right, it's an equality. How do you prove the equality of two sets in mathematics? So any mathematician will tell you almost instantly, well, you first prove the inclusion on one side and then you prove the inclusion on the other side. And if you do both inclusions, then you get equality. So then you can start with the inclusion on one side. You can ask, is the original relation included in the join? This is actually trivial. Yeah, I usually don't do that. You know, what happens when people don't want to prove something, they just, okay, it's left as an exercise, just do it at home, right? But actually, it's really something that you can see intuitively, because if it's in the original relation, then you get the some tuple like A, B, C, D, E. You get the projection of that tuple in the two sub-relations. For example, here you have small a, small b, small c, small d. Then you're going to have small a and small d on the left, and you're going to have small a, small b, and small c on the right, right? But then if you join these things, it's going to combine all of the tuples with all of the tuples. In particular, it's going to combine AD with ABC, getting back ABCD, right? So you see that if you start with a tuple in the original relation and project and join back, then you get it back in the join, right? For whom is that clear, more or less? It's normally intuitive. And otherwise, think about it again, right? So this is really the easy side, right? If it's in the original relation, it's almost by construction that it's going to come back through the join. Okay, but it's the other side that is actually not trivial at all. If I pick a tuple in the join of these two tables, so the AD table and the ABC table, if I join them back and I pick a tuple in the join, is that tuple in the original relation? That's the inclusion the other way around. So we can reason a little bit with that. So let's take then a tuple in the join, right? And I insist a tuple in the join, not in the original relation. So this tuple right here, ABCD, that I take now, I'm assuming this is somewhere in the join of AD and ABC. So if it's in the join, then necessarily the projection must have come from the tables that you join, right? Otherwise, it wouldn't be in the join. So if ABCD is in the join, then it must be that AD was in the projection and ABC was in the projection, right? We just don't know if ABCD was in the original table, right? If they got projected from the same tuple. So here's the trick. You have now these two tuples that you know are actually in the two subtables. So you know that since you have that in the join, then you have somewhere in this table AD, you have small a, small d. And somewhere in the table on the right, you have small a, small b, small c, right? And I just pick the letters arbitrarily. Then I'm going to write things like that. It means that if I have AD here, and if I have ABC here, they must come somewhere from the original relation. Let's start with AD. If we have AD here, they must be a tuple, let's call it T1, in the original relation that got projected to AD. And I don't know what's in there, I don't know what's in there, but there was a tuple somewhere here that got projected to AD. So it has value A here and D here. Then this ABC also has to come from somewhere in the original relation. So there must be some tuple, T2, that has A, B, and C in there, that got projected there, but then I don't know what there was in D. I'm leaving it empty. You know the trick here, what's important. I don't know if this is the same tuple. I don't know. Maybe T1 and T2 are different tuples that got projected to AD and ABC. I don't know, right? I want to prove it. I want to actually find out, right? So this, what you see here, is basically a subset of my original relation. I know that somewhere I have AD and somewhere else I have ABC, but here I leave the values empty, and maybe there's plenty of other tuples, but in particular these two. Now, I want to find out if I can infer from this here that ABCD as a single tuple is in the original relation. How do you think I can do that? We have knowledge here, we know things, right? What do we know? Remember how I decomposed that? I had a functional dependency that A gives me D, right? So what can I do with that functional dependency? So let me put letters here, right? So I don't know what's in there. Let's call it B1, C1, and D2. I'm adding that here. What can I conclude from my functional dependency that A gives me D? Zoom, maybe? What can I conclude here? Yes, I see over there. Yes, so exactly. I'm going to repeat because it wasn't in the microphone. So you just said that because A functionally determines D, then D must be equal to D2, right? This is what you said. These two values must be the same. How do I know? Because these two are the same. It's A and A. And since I know that A gives me D, then it must be that these are the same. This is what a functional dependency is. So what can I do? I can just drop the two here, right? I know that these are the same, so I know that I have D here. Do you see that we are hitting the jackpot now? Here, see, A, B, C, D. We've just proven that A, B, C, D is in the original relation. It was in the join. We inferred that we had AB, AD, and ABC. We inferred that there must have been two tuples in the original relation looking like that. We fill in the blanks with fake variable names like B1, C1, D2, arbitrary. We use functional dependencies in order to try to remove the subscripts here. And we hit the jackpot if we get, it's really like it's literally a bingo, right? You really try to get everything on the same line. This is literally what this is about. And so here we have a line with everything. So we won. We proved that T is in the original relation. Sometimes it works, then you hit the jackpot. Sometimes you don't. And then you're stuck, and it means that you cannot prove that the join is the same as the original relation, then you lost information. Okay, who can feel that they can do that for any examples? If I give you other decompositions, other functional dependencies, more complex, some of you. There will be exercises, right? You will get plenty of exercises, plenty of different tables to exercise on. It typically appears at the exam also that we give you a few questions. Maybe not every year, but some years you get some chase grids to complete a little bit. Okay, we give you several grids and you ask which is the correct one. Okay, so we're almost done now with this theory. So what did we do? We took a relational table. It wasn't in Boyce code normal form because there are functional dependencies we don't like because the left-hand side is not a super key. So we use that functional dependency that gives us a decomposition using the left-hand side that wasn't a super key as a join key, right? As a join criterion that acts as foreign key and primary key. Then we have the decomposition. We use the chase algorithm to see if we lose or not information. Right, so we call it a lossless join. We didn't lose information. And we iterate until we get only tables in Boyce code normal form, right? And what we don't have necessarily is the preservation of dependencies, right? It might be that we lose some functional dependencies in the process, bad luck, right? So this is the part we lose. You might have constraints that you could enforce on the bigger table that you can no longer enforce on the decomposed table. So it's a compromise to make here. It's actually an impossibility triangle that you cannot have both Boyce code normal for everywhere and lossless joins and dependency preservation. So you have to give up that one for the Boyce code normal form decomposition, right? But if you change, you can also do other ways, right? You can have Boyce code normal form and dependency preservation, but then you don't have the lossless join, or you can have lossless join and dependency preserving, but you don't get the Boyce code normal form, right? But it turns out that there's other normal forms. I'm not getting into them, right? There's second normal form, third normal form, fourth normal form, and so on. So you could downgrade to the third normal form and then get back these properties there, right? It's just a weaker normal form. This is actually the final slide. database design theory, you survived. You see, that was probably the toughest part of the entire lecture, right? So if you survive that, you're good for the rest of the semester, right? Who enjoyed this theory? That's actually cool math, right? Okay. Any questions, or otherwise we move on? We move on then? Okay, more practical parts. All right, so what I'm going to do is I stop the recording, see you on the other side, just for a few seconds.